Hello, in this video we'll be going over a fascinating aerodynamics device known as a Gurney Flap. So first we'll go over what is a Gurney Flap. A Gurney Flap is a small plate added perpendicularly to the end of an airfoil. So you can see on this Newman airfoil right here that the Gurney Flap is the small plate protruding underneath the airfoil. The height is usually going to be about 1 to 5% of the airfoil's chord, and it's used to increase the lift, while with the sacrifice being that it does create more drag. The Gurney Flap was invented by Dan Gurney, who was a Formula One driver and engineer who competed from the years of 1959 to 1970. He also competed in IndyCar, NASCAR, and the 24 Hours of Le Mans race. He was born in 1931 and unfortunately he died in 2018. In 1990, he was inducted into the International Motorsports Hall of Fame, and in 1971, the Gurney Flap was first used for Gurney's All-American Racers team for the Indianapolis 500 race. So the next obvious question is, what does a Gurney Flap actually do? So what it's going to do is it's going to increase the coefficient of lift, the coefficient of drag, and the pitching moment, and it will decrease the angle of attack for zero lift. So these two graphs are from a CFD run I did on a N10-IL airfoil, a Reynolds number of 100,000. And as we can see, in both cases, orange represents the Gurney Flap and the blue line represents the airfoil with no Gurney Flap. And we can see that, as expected, the drag coefficient for any given angle of attack is going to be higher with the Gurney Flap, and the lift coefficient will also be higher with the Gurney Flap. Now, how does a Gurney Flap actually work aerodynamically? So right here are the velocity path lines from that same CFD run I did earlier, and this is an absolute pressure contour. Both of these are an N10-IL airfoil at a Reynolds number of 100,000 with a Gurney Flap. And what we can see happening right here is that the air is slowing down in front of the Gurney Flap, and this is causing a zone of high pressure to occur in front of the Gurney Flap and a zone of low pressure to occur behind the Gurney Flap. And what's happening is this low pressure zone is so strong that the air particles are getting pulled along, and then they're actually getting pulled, after they pass the airfoil, getting pulled back into this recirculation zone right here. And this is going to speed up the air along the bottom, and this is going to lead to a higher coefficient of lift. For those of you wondering, the reason why this airfoil looks upside down is because a lot of my experience is in Formula SAE, where the airfoils are going to be upside down because we're more interested in downforce than lift. But obviously this is going to work the exact same way for if you place it on an airplane. And right here is just more proof what we were saying about the pressure. As we can see, we have a darker red right here and a lighter red right here. So we're having more pressure built up at the front of the Gurney Flap than at the rear. Here are a couple of common uses of Gurney Flaps. For instance, they're commonly used on helicopters, race cars, banner towing airplanes. It's going to be a lot of applications where you're at like a lower speed, where you need a lot of lift and maybe drag isn't so much as important. So right here we obviously have a picture of a Gurney Flap on a car and on a helicopter. Thanks to you all for watching this video on Gurney Flaps. Here are my text sources. I'll also have them down in the description below. And here are my image sources. And anyway, I hope you enjoyed this video, and if you have any questions or suggestions, please leave them in the comments below.